In mathematics, model theory is the study of classes of mathematical structures from the perspective of mathematical logic. The objects of study are models of theories in a formal language. We call a set of sentences in a formal language a theory. A model of a theory is a structure that satisfies the sentences of that theory. Model theory recognizes and is intimately concerned with the duality. It examines semantical elements by means of syntactical elements of a corresponding language. To quote the first page of Chang and Keisler, universal algebra plus logic equals model theory. Model theory developed rapidly during the 1990s, and a more modern definition is provided by Wilfred Hodges. Model theory equals algebraic geometry minus fields, although model theorists are also interested in the study of fields. Other nearby areas of mathematics include combinatorics, number theory, arithmetic dynamics, analytic functions, and non-standard analysis. In a similar way to proof theory, model theory is situated in an area of interdisciplinarity among mathematics, philosophy, and computer science. The most prominent professional organization in the field of model theory is the Association for Symbolic Logic. Branches of model theory. This article focuses on finitary first-order model theory of infinite structures. Finite model theory, which concentrates on finite structures, diverges significantly from the study of infinite structures in both the problems studied and the techniques used. Model theory in higher-order logics or infinitary logics is hampered by the fact that completeness does not in general hold for these logics. However, a great deal of study has also been done in such languages. Informally, model theory can be divided into classical model theory applied to groups and fields, and geometric model theory. A missing subdivision is computable model theory, but this can arguably be viewed as an independent subfield of logic. Examples of early theorems from classical model theory include Gödel's completeness theorem, the upward and downward Löwenheim-Skolem theorems, Vort's two-cardinal theorem, Scott's isomorphism theorem, the emitting types theorem, and the Ril-Nardzewski theorem. Examples of early results from model theory applied to fields are Tarski's elimination of quantifiers for real closed fields, Axe's theorem on pseudo-finite fields, and Robinson's development of non-standard analysis. An important step in the evolution of classical model theory occurred with the birth of stability theory, which developed a calculus of independence and rank based on syntactical conditions satisfied by theories. During the last several decades, applied model theory has repeatedly merged with the more pure stability theory. The result of this synthesis is called geometric model theory in this article. An example of a theorem from geometric model theory is Reshkovsky's proof of the Mordell-Lang conjecture for function fields. The ambition of geometric model theory is to provide a geography of mathematics by embarking on a detailed study of definable sets in various mathematical structures. Aided by the substantial tools developed in the study of pure model theory, universal algebra. Fundamental concepts in universal algebra are signatures sigma and sigma algebras. Since these concepts are formally defined in the article on structures, the present article can content itself with an informal introduction which consists in examples of how these terms are used. The standard signature of rings is sigma ring equals times, plus, minus, 0, 1, where times and plus are binary, minus is unary, and 0 and 1 are nullary. The standard signature of semi-rings is sigma SMR equals times, plus, 0, 1, where the arities are as above. The standard signature of groups is sigma GRP equals times, minus 1, 1, where times is binary, minus 1 is unary and 1 is nullary. The standard signature of monoids is sigma MND equals times, 1, A ring is a sigma ring structure which satisfies the identities U plus equals plus W, U plus V equals V plus U, U plus 0 equals U, U plus E equals 0, U times equals times W, U times 1 equals U, 1 times U equals U, U times equals plus and times U equals plus. A group is a sigma GRP structure which satisfies the identities U times equals times W, U times 1 equals U, 1 times U equals U, U times U minus 1 equals 1 and U minus 1 times U equals 1. A monoid is a sigma MND structure which satisfies the identities U times equals times W, U times 1 equals U and 1 times U equals U. A semigroup is of times structure which satisfies the identity U times equals times W. A magma is just a times structure. This is a very efficient way to define most classes of algebraic structures, because there is also the concept of sigma homomorphism, which correctly specializes to the usual notions of homomorphism for groups, semigroups, magmas and rings. For this to work, the signature must be chosen well. Terms such as the sigma ring term T given by plus are used to define identities T equals T, but also to construct free algebras. An equational class is a class of structures which, like the examples above and many others, is defined as the class of all sigma structures which satisfy a certain set of identities. Birkhoff's theorem states, a class of sigma structures is an equational class if and only if it is not empty and closed under subalgebras, homomorphic images, and direct products. An important non-trivial tool in universal algebra are ultraproducts, where I is an infinite set indexing a system of sigma structures I, and U is an ultrafilter on I. While model theory is generally considered a part of mathematical logic, universal algebra, which grew out of Alfred North Whitehead's work on abstract algebra, is part of algebra. This is reflected by their respective MSc classifications. Nevertheless, model theory can be seen as an extension of universal algebra. Finite model theory. Finite model theory is the area of model theory which has the closest ties to universal algebra. Like some parts of universal algebra, and in contrast with the other areas of model theory, it is mainly concerned with finite algebras, or more generally, with finite sigma structures for signatures sigma which may contain relation symbols as in the following example. The standard signature for graphs is sigma grph equals E, where E is a binary relation symbol. A graph is a sigma grph structure satisfying the sentences in. A sigma homomorphism is a map that commutes with the operations and preserves the relations in sigma. This definition gives rise to the usual notion of graph homomorphism, which has the interesting property that a bijective homomorphism need not be invertible. Structures are also a part of universal algebra. After all, some algebraic structures such as ordered groups have a binary relation less than. What distinguishes finite model theory from universal algebra is its use of more general logical sentences in place of identities. The logics employed in finite model theory are often substantially more expressive than first-order logic. The standard logic for model theory of infinite structures. First-order logic. Whereas universal algebra provides the semantics for a signature, logic provides the syntax, with terms, identities and quasi-identities. Even universal algebra has some limited syntactic tools. First-order logic is the result of making quantification explicit and adding negation into the picture. A sentence is a formula in which each occurrence of a variable is in the scope of a corresponding quantifier. Examples for formulas are phi to mark the fact that at most x is an unbound variable in phi, and psi defined as follows. It is intuitively clear how to translate such formulas into mathematical meaning. In the sigma SMR structure of the natural numbers, for example, an element n satisfies the formula phi if and only if n is a prime number. The formula psi similarly defines irreducibility. Tashi gave a rigorous definition, sometimes called Tashi's definition of truth, for the satisfaction relation, so that one easily proves is a prime number, is irreducible. A set T of sentences is called a theory. A theory is satisfiable if it has a model, i.e., a structure which satisfies all the sentences in the set T. Consistency of a theory is usually defined in a syntactical way, but in first-order logic by the completeness theorem there is no need to distinguish between satisfiability and consistency. Therefore model theorists often use consistent as a synonym for satisfiable. A theory is called categorical if it determines a structure up to isomorphism, but it turns out that this definition is not useful, due to serious restrictions in the expressivity of first-order logic. The Löwenheim-Skolem theorem implies that for every theory T which has an infinite model and for every infinite cardinal number kappa, there is a model such that the number of elements of is exactly kappa. Therefore only finitary structures can be described by a categorical theory. Lack of expressivity has its advantages, though. For model theorists, the Löwenheim-Skolem theorem is an important practical tool rather than the source of Skolem's paradox, in a certain sense made precise by Lindström's theorem. First-order logic is the most expressive logic for which both the Löwenheim-Skolem theorem and the compactness theorem hold. As a corollary, the compactness theorem says that every unsatisfiable first-order theory has a finite unsatisfiable subset. This theorem is of central importance in infinite model theory, where the words by compactness are commonplace. One way to prove it is by means of ultraproducts. An alternative proof uses the completeness theorem, which is otherwise reduced to a marginal role in most of modern model theory. Axiomatizability, elimination of quantifiers, and model completeness. The first step, often trivial, for applying the methods of model theory to a class of mathematical objects such as groups, or trees in the sense of graph theory, is to choose a signature sigma and represent the objects as sigma structures. The next step is to show that the class is an elementary class, i.e., axiomatizable in first-order logic. E.g., this step fails for the trees, since connectedness cannot be expressed in first-order logic. Axiomatizability ensures that model theory can speak about the right objects. Quantifier elimination can be seen as a condition which ensures that model theory does not say too much about the objects. A theory T has quantifier elimination if every first-order formula phi over its signature is equivalent modulo T to a first-order formula psi without quantifiers, i.e., holds in all models of T. For example, the theory of algebraically closed fields in the signature sigma ring equals has quantifier elimination because every formula is equivalent to a Boolean combination of equations between polynomials. A substructure of a sigma structure is a subset of its domain, closed under all functions in its signature sigma, which is regarded as a sigma structure by restricting all functions and relations in sigma to the subset. An embedding of a sigma structure into another sigma structure is a map F, a B between the domains, which can be written as an isomorphism of with a substructure of. Every embedding is an injective homomorphism, but the converse holds only if the signature contains no relation symbols. If a theory does not have quantifier elimination, one can add additional symbols to its signature so that it does. Early model theory spent much effort on proving axiomatizability and quantifier elimination results for specific theories, especially in algebra. But often instead of quantifier elimination a weaker property suffices. A theory T is called model complete if every substructure of a model of T which is itself a model of T is an elementary substructure. There is a useful criterion for testing whether a substructure is an elementary substructure, called the Tashi-Vort test. It follows from this criterion that a theory T is model complete if and only if every first-order formula phi over its signature is equivalent modulo T to an existential first-order formula, i.e., a formula of the following form, where psi is quantifier-free. A theory that is not model-complete may or may not have a model completion, which is a related model-complete theory that is not, in general, an extension of the original theory. A more general notion is that of model companions. Categoricity. As observed in the section on first-order logic, first-order theories cannot be categorical, i.e., they cannot describe a unique model up to isomorphism, unless that model is finite. But two famous model-theoretic theorems deal with the weaker notion of kappa categoricity for a cardinal kappa. A theory T is called kappa categorical if any two models of T that are of cardinality kappa are isomorphic. It turns out that the question of kappa categoricity depends critically on whether kappa is bigger than the cardinality of the language. For finite or countable signatures, this means that there is a fundamental difference between cardinality and kappa cardinality for uncountable kappa. A few characterizations of categoricity include: for a complete first-order theory T in a finite or countable signature, the following conditions are equivalent. T is categorical. For every natural number n, the stone space Sn is finite. For every natural number n, the number of formulas phi in n free variables, up to equivalence modulo T, is finite. This result, due independently to Engler, Rylnarzewski and Svenonius, is sometimes referred to as the Rylnarzewski theorem. Further, categorical theories and their countable models have strong ties with oligomorphic groups. They are often constructed as Frase limits. Michael Morley's highly non-trivial result that there is only one notion of uncountable categoricity was the starting point for modern model theory, and in particular classification theory and stability theory. Morley's categoricity theorem: if a first-order theory T in a finite or countable signature is kappa categorical for some uncountable cardinal kappa, then T is kappa categorical for all uncountable cardinals kappa. Uncountably categorical theories are from many points of view the most well-behaved theories. A theory that is both categorical and uncountably categorical is called totally categorical. Model theory and set theory. Set theory, if it is consistent, has a countable model. This is known as Skolем's paradox. Since there are sentences in set theory which postulate the existence of uncountable sets and yet these sentences are true in our countable model, particularly the proof of the independence of the continuum hypothesis requires considering sets in models which appear to be uncountable when viewed from within the model, but accountable to someone outside the model. The model-theoretic viewpoint has been useful in set theory, for example in Kurt Gödel's work on the constructible universe, which, along with the method of forcing developed by Paul Cohen, can be shown to prove the independence of the axiom of choice and the continuum hypothesis from the other axioms of set theory. In the other direction, model theory itself can be formalized within ZFC set theory. The development of the fundamentals of model theory rely on the axiom of choice, or more exactly the Boolean prime ideal theorem. Other results in model theory depend on set theoretic axioms beyond the standard ZFC framework. For example, if the continuum hypothesis holds, then every countable model has an ultra power which is saturated. Similarly, if the generalized continuum hypothesis holds, then every model has a saturated elementary extension. Neither of these results are provable in ZFC alone. Finally, some questions arising from model theory have been shown to be equivalent to large cardinal axioms.